Понятно. Участники. Вот. Пока что, видишь, я отключил.
Dear colleagues, dear participants, I will be short to start our online courses. In spite of we live in very hard and difficult times when awful things happened, nevertheless, we can try to do our best in all the fields in which we work or live. Therefore, I hope that today online courses will be very useful for you. I think that these courses cover some very important areas of chemometrics knowledge, including multidimensional analysis, which is devoted to which is devoted the first courses. Independent component analysis, the one of the most popular technique to analyze NMR data or spectroscopy data in near infrared range. And finally, you can learn a lot about application of electronic noise, of multi-channel sensors based on electrochemical cells. Thus, I think I said all that I want, and I hope that Ivan is ready to start the first courses. Ivan, I'm happy to introduce the most advanced person in analysis of multivariate data. I think it's very, in spite of his age, he's very prominent in this field. And you are welcome, Ivan.
Okay, this first slide is just to let everyone know whether the screen sharing is working. Okay, I think that it's working for everyone. I'm also dropping this link in the chat. It's mostly useless for now, but if someone gets disconnected or everyone gets disconnected, you can at least get the slides there. And after the course, I intend to share the recording with everyone, and the link will be there. So let's start. My name's Ivan. We'll be talking about PARAFAC today, and specifically PARAFAC and fluorescence excitation-emission spectroscopy. I'll start with the basics. And if you have any questions, I think it's better to ask me right away. This way, the course will be more interactive and less the way some courses are, when you just sit in front of the monitor and speak words at the LED and the camera and hope you're heard. You can even use voice, but I'll be looking at the chat too. We'll also start with the theory. So you don't have to do anything now, just watch and relax. We'll discuss why we use PARAFAC, which is also called canonical tensor decomposition, if you want to be fancy. We'll discuss why it doesn't actually fit fluorescence and the kind of things we'll have to do to make it fit. And we'll also discuss how to make sure that we've chosen the right model, because there's always a few options. when it comes to choosing the number of components, for example. Then we'll start practicing, but this will come later. So, excitation-emission matrices. They're called matrices, so you know there's two independent variables, and the two variables are excitation wavelength and emission wavelength. By varying the excitation wavelength, we can observe different emission spectra of our sample, and the result looks more or less like the image on the right on the slide. It's a surface, it's a function of two variables. It contains some features that are fluorescence and some features that are not. The reason it looks mostly like this is this Jablonski diagram. By applying different excitation spectra, we can excite the particles or fluorophores. They undergo the transition from the basic electron state to an excited electron state. But then before emitting the light, they undergo non-radiative transition to the first base excited states, which decouples the excitation and emission spectra and makes them independent. This is important because despite we have whole matrices, they can be factored in the independent spectra, which will be important later. Is there a question or is it just noise? I guess it's just noise. Okay. So since the excitation spectrum is independent from the emission spectrum, because the source level for the transition is independent from the target level for the transition, we can say that fluorescence is an outer product. It's proportional to the oh crap. I think I pressed something wrong. I'm sorry. Okay, so fluorescence is an outer product. It's the signal we observe is proportional to the excitation spectrum, and it's proportional to the emission spectrum. If we have more than enough fluorophore in our spectrum, which we usually do, it's a sum of outer products. One outer product is added directly to the other outer product. This image still has a lot of symmetry in it. We'll be using this mathematical property a lot. If we combine the same fluorophores in different amounts, we get this image. I hope you can see that, for example, this fluorophore and this fluorophore, they have the same coordinate along the emission wavelength. It's here. Also here. But they're present in different concentrations, which means that they give different results in samples. But since they're the same fluorophores, they have the same excitation spectrum shape and the same emission spectrum shape. We can write down the expression for the fluorescence of a given sample as a function of a small amount of information. This is basically the PARAFAC equation. It's a sum of independent factors proportional to a function of the sample axis, of the emission wavelength axis, and the excitation wavelength axis. This means that we can use PARAFAC to model fluorescence, assuming under certain assumptions which don't always hold. There is one other reason why PARAFAC is so useful, but we'll start a bit far away from it and then approach PARAFAC. Suppose I'm brewing tea. I'm not a morning person, I brew a lot of tea. Suppose it's pu'er tea specifically, and it's the only component in the solution. It's just water and whatever can be extracted from the tea. In that case, there is an easy way to determine the concentration. Just measure the total absorbance of the sample. As long as I have a blank and C is the only thing in the solution, I don't even have to choose a certain wavelength. I can just use whatever. It will be proportional to the concentration of the T. Of course, this doesn't handle interference by definition, because we're assuming we have a selectivity. So if someone's being very confused and added T to my sample, then it's an interference, and I cannot determine the concentration of the pu'er T using the same linear regression as I did. And of course, we don't have to use simple univariate linear regression in that case. Multivariate linear regression lets us handle interference as long as they have different spectra. For example, pu'er T has a very prominent spectral feature here. Oh my. And T has a prominent spectral features here. We can calibrate our multivariate linear regression in order to handle this, at the cost of making every sample a vector of absorption coefficients at different wavelengths. But as long as we place, what? Is there a question? I guess there isn't. If there is, let me know in the chat. As long as we place all the interference in the training, in the calibration set, we can handle them. And we can use PLS regression, we can use regularization and multivariate regression, we can use whatever. In the end, we get regression coefficients. And you can see that the pu'er region is taken into account, and the Ulun region is subtracted from the resulting concentration estimate in order to handle the interference. Okay, but suppose someone adds green tea into my sample, and they didn't know that, and they didn't take that into account by adding it to the calibration data set. This is a problem, because now my Now my regression coefficients cannot be used to determine the concentration of poor. We have the same problem as above. But if we try to solve for a known interference, which we could by using multivariate curve resolution, by saying that, okay, maybe this is green C, maybe. We'll add an extra column in here just in case. It turns out that multivariate curve resolution is not unique. For example, let's say that we had a mixture of T's, not that people normally do that, but let's say we do. And we're interested in poor. We're trying to handle interference, green C and lone C. And if we have a multivariate curve resolution solution, which is two matrices, a matrix of concentration and a matrix of individual pure spectra, we can always insert an invertible matrix between them, then invert it, then join them together. And it will give us a new solution, indistinguishable from the original solution. MCR usually tries to handle this problem by having a lot of information of different kinds and by imposing constraints, like a spectrum cannot be negative, which makes sense. But in our case, we just have absorbance, and lone C and green C spectra are very similar. So we can rotate our solution by inserting these arbitrary invertible matrices a lot. The resulting pure spectra look like this. They all overlap, except here, but everywhere else they overlap. And of course, the concentration profiles are also very different. It's impossible to predict concentrations from this information. But if we switch to second order data, suddenly we don't have this problem anymore. Suppose we have two samples and we're interested in this analyte here, but the second sample also has some kind of interferent here. The interesting thing about PARAFAC is that as long as the data is second order in the sense that it consists of sums of outer products, it has this symmetry that the resulting image is a sum of products of excitation profiles and emission profiles. As long as it stands, we can just throw the data in PARAFAC and it will separate the interferent from the analyte. So despite the MCR problem did not have a unique solution, even with all the constraints, PARAFAC is structured in such a way that there is a unique solution to the PARAFAC problem, despite it's so similar to MCR. It's just a three-way MCR. This is probably helped a lot by the fact that the fluorescence model that we discussed a bit before is very similar to the PARAFAC equation. We can just correlate. These are concentrations, these are emission profiles, these are excitation profiles. It's the same. So if we stack our excitation emission matrices into a data cube, we can factor it into concentrations, even if we don't know whether we have interference or not. Of course, there is a star. It's more unique than MCR, but there are still problems. Of course, there's always problems. Now, I've been telling you that fluorescence is the same as PARAFAC, and it's been a bit of a lie, because what we observe in our fluorescence measurements may not directly adhere to the PARAFAC model for two reasons. One is, look at these samples. They're not really transparent. They absorb a lot of light. They will absorb the excitation light, and they will absorb the emission light, and this will disturb the picture and make the signal not true linear. The other reason is scattering. And the problem with scattering is that it doesn't adhere to the PARAFAC model at all, unlike fluorescence. So something has to be done about scattering signal too. Inner filter effect is, I think, simpler. I mean, we shine some light. It's just happens. We shine some light. It gets absorbed. The fluorescence signal is emitted, but it also gets absorbed. And what we see is a result of these two processes. And since everything gets absorbed, and instead of a straight line dependency between concentration and fluorescence intensity, we get something curved. And in extreme cases, the line also goes down. But there is a simple way to control that. Since what we observe is partially absorbed, we can just multiply this back. We'll take this factor that distorts the image and add the plus here instead of minus, and multiply the image back. It's also kind of an outer product, but the problem with this, it's a different outer product for every image. So even if we manage to describe this with a PARAFAC model, we'll get very distorted excitation and emission spectra. So it's a good idea to handle this before modeling. But once we multiply the spectrum back, we're usually good. Another method that's sometimes used is controlled dilution approach. In that case, we don't have measured absorbance spectra. They would usually be here, but we don't know them. But we do know that whatever we measure consists of the already known PARAFAC compatible fluorescence signal and a bunch of absorbance, could be more than once, that absorb the signal on both wavelengths. In that case, we can dilute the sample. And we know that the only place where the intensity changes is here in the concentrations of fluorophores, and here in the concentration of absorbers. And once we divide both concentrations by P, by diluting, we can factor the dilution factor outside. We can also factor this outside because it's a product, and we know the properties of products. And this is very similar to the original equation. We have this term here. It's more or less unchanged. We have this term here, and it's also unchanged. So let's call this F0, the original fluorescence. And let's call this Z for density. We have the undiluted sample, which consists of original fluorescence and density. We have diluted sample, which also consists of original fluorescence and density, but combined in different ways. And they're both unknown, but we have two equations and two unknowns. We can solve for them. The solution could look a bit scary, but it has only to be done once. And if you want to be really fancy, you can measure multiple dilution spectra, a dilution series, and fit the original fluorescence and the absorption spectrum as parameters in a function of the dilution factor. So this is the solution for 2 points. And if you have more than 2 points, you can use regression. It will give you the answers. Personally, I haven't been using controlled dilution approach because I've been mostly working with seawater, and seawater samples are very dilute already. But I know that in, let's say, sugar production, they have to be using an approach like this. As an aside, in some cases, like fluorescence of mineral oil, there is even more problems. Like one fluorophore could be absorbing light from a different fluorophore and emitting on this wavelength. Suppose we have a emission spectrum here and excitation spectrum. Okay, this is excitation spectrum, this is emission spectrum, and they overlap. This means that we could be exciting one fluorophore and see the light of a different fluorophore. This only happens at very high concentrations of fluorophores, and there's no good way to fix that. So if you want your spectra to adhere to a PARAFAC model, you'll probably have to dilute them. The other major problem in PARAFAC modeling is scattering. And it's a problem because unlike fluorescence, which is like this, it can be factored. Unlike fluorescence, scattering just cannot be factored into two factors, because on every excitation wavelength, the emission spectrum is shifted, it's different. And on every emission wavelength, the excitation spectrum is also different. There has been experimental work by Osman Drinan, for example, where he took a diagonal line of a scattering signal and tried to shift it until it looked like a straight line, which could be factored into two factors looking like this. But in many cases, it doesn't work so well. And it's a problem with ongoing research in it. So what can we do instead of trying to factor the scattering signal? We can remove it, of course. It's relatively easy for PARAFAC to handle missing data because we can just set the area weight in this area to 0. Essentially, we're telling PARAFAC, I don't care what you invent for this area of the image, as long as the rest of the image is consistent with it. So if we have only one factor and it looks like this, but we also remove this strip because we think there's scattering, PARAFAC will usually give you a very consistent answer because there's only one solution for this part. There is one solution for this part. There's nothing creative here to invent. But once you get a lot of components or large unknown areas, imagine that the emission axis stretches here, and we continue this large unknown area, and it's unknown in all samples. PARAFAC will be free to invent anything, including physically impossible solutions. But if you keep the anti-stocks area, which is sometimes not even measured at all, if you fill it with zeros, like here, there was nothing, but we added zeros. And if you keep the unknown areas small in size, not large, this is a relatively straightforward solution to the scattering signal problem. But if you do leave them large, then PARAFAC will be slow. It will give you strange solutions. It may get stuck in local minima and so on. Since missing data can pose a problem, maybe we can interpolate them. This is not a beautiful solution because only PARAFAC can model PARAFAC. And we're trying to bring something else. Why? But this is a pragmatic solution because it prevents PARAFAC from getting stuck trying to model something uninteresting to you. There's usually no fluorescence in the scattering area. So if we can fill it with something realistic, it's okay. The downside of interpolating the scattering area is having to choose the interpolation method. Here is a 6 I could just name offhand. There's probably more, and everyone has their favorite. Some of them, like p-chip, they're very simple. They work row by row. They try to interpolate it in a, in a piecewise monotonic way. And there is no parameters to set. On the other hand, let's say Lois, it does something different. It looks at the grid of all the points we have available. And if it's asked to fill the void here, for example, it takes neighbors of every point, and it fits some kind of polynomial surface through every one of them. And there is a parameter which defines the size of the neighboring area that's taken into account. And if you choose it too large, the interpolated values will be too smooth and won't work, will look realistic, and it wouldn't even connect to the rest of the spectrum. But if you choose the neighbor area too small, it will also look unrealistic because there will be jumps in the signal and the solutions will be unstable. And it's a lot of trade-offs, unfortunately. Here is an example of a bit noisy spectrum with 3 different interpolations. I could say that Lois is a bit too smooth here. You could notice the artifacts, which look like horizontal lines because p-shape works line by line. And unfortunately, it's a bit sensitive to noise. So if you have an image that looks like that. Then a gap and some more noisy image. It sees this jump in the value and it tries to fit it like this, but then goes smooth and approaches the rest of the line. So P-chip is sensitive to noise, but otherwise really simple. And if it works, maybe it's just good enough. Wood-tacker smoothing is my personal favorite. I could give a whole separate talk on just wood-tacker smoothing. It works by minimizing two factors. One of them is one of them says that the smooth surface must be close to the original surface, and the other says that it also must be smooth. The beauty of wood-tacker smoothing is that by choosing this term, you can influence the resulting surface. Like you can put first order differences or second order differences or third order differences with different combinations of lambda factors. I think you could choose lambda factors to model fluorescence really well. At least the parts that we have to interpolate, like here and here. But on the other hand, if you choose the lambda values wrong, you'll get wrong answers. So interpolation is nice, but it's a trade-off. What else? Okay, there is an experimental work. I'll be giving a talk about this on, is it Wednesday or Thursday? I think it's Wednesday. Where we know that fluorescence looks like this. We know that scattering cannot be factored. So let's say we don't want to factor scattering, and just try to model our tensor as a sum of fluorescence and scattering signals. It's experimental in the sense that I don't have a proof that this solution is unique. But in my experiments, as long as there's only one scattering component, the solution is actually unique. But on the other hand, you might have to add more than one scattering component, despite it sounds like nonsense. In some data sets just cannot be described any other way. But if you're lucky, and this was a really low quality and noisy data set, but we managed to separate fluorescence and scattering, and there's no fluorescence here in the scattering component. And I think we handled scattering really nicely. So maybe if I develop it further, it could be a good approach. Okay, suppose we handled all of this and our data looks like PARAFAC, but now we have to choose the number of components. And this is a bit painful because this is the PARAFAC equation. We can always multiply this and this and this. And as long as their product is 1, we'll get the same model as before. So we cannot rotate solutions, but we can rescale them. We can also permute components. We can change places between components 1 and 3, and the model will also be the same. So despite being unique in one sense, PARAFAC is not unique in others. But even if we take that into account, of course, we cannot just keep adding components on top of other components. The components will eventually start looking like noise and will be describing noise. And since PARAFAC is not additive like principal component analysis, adding another component might break all your previous components. So a 5-component model could be meaningful, but adding a 6th component may destroy the 5 previous components too. They will all be non-meaningful. But we have to choose the number of components. And the way we usually do it in regression is that we have some kind of function. We have our predictors. We want to predict some regressor value, some y. So by performing cross-validation, we can just stuff new X data and look at the resulting Y data and compare it to the right answers, to the ground truth. But this is PARAFAC. There is no Y value to predict. This is exploratory data analysis. So the only thing we can do is compare models to other models. Which is a bit unfortunate because I think it's easier to get wrong. And when it comes to, when it comes to splitting data and comparing the resulting PARAFAC models, there are 2 ends of the spectrum. We can either take one sample out of the model and perform leave one out cross-validation, which is called jackknifing in PARAFAC. On the other end of the spectrum, we can take a whole half, then model them both and compare. We cannot take more than a half because then we'll be taking like 49% on the other end. This stylus is, I think it's broken. I'm sorry. So let's start with leave one out cross-validation. We take each sample out of the model. We fit the model without the sample. We get some kind of scores and loadings. What we can do after that is take the resulting loadings, like let's say we had a data cube. I think I hear a Danish train in the background. Okay, never mind. Let's say we have a data cube and we take one sample out of it. And the resulting model gives us excitation spectra and emission spectra. We can use those to find out the scores, the concentrations of each fluorophore for the sample that we took out of the model. And there is a few things we can do. I'm mostly following this paper on PARAFAC jackknifing. The simplest would be comparing the scores between the overall model and the model where you're taking each sample out and trying to fit the rest of it. Supposedly, if there are outliers in the data set, they'll influence, by taking them out, you'll see a large difference in excitation and emission profiles. And when you try to fit the emitted sample back, you get very different scores from the overall model. So here, the sample that's labeled K looks a bit of like an outlier, because by taking out its loadings, you change the scores. But maybe it's just noise in the data set. It's not too far from the straight line. And when I was simulating this data set, I didn't include any outliers. But if you get a sample that's, let's say, here, that's definitely an outlier. Something's going on in the model. You can also look at the individual loadings that you get by taking out samples out of the model and fitting the rest of it. It can give you an idea of how stable the solution is, how uncertain the solution is. For example, here maybe the noise got into the model. This is definitely not right, but we can be relatively sure about the rest of the profiles. Also here, we may be having local minima. But if you perform jackknifing and for every sample you take out of the model, the shape of the resulting loading stays the same, that should give you a reason to trust your models a bit more. On the other end of the spectrum, we have split half validation, which is to say we had a data cube, we split it into two, we fit them and compare them. Also very much like in cross-validation, or like in k-fold cross-validation, for example. The problems start when you consider every part of this idea. For example, PARAFAC is not unique in the sense that it can be reordered and rescaled. So the components can be coming in different orders. Like one of your halves gives you components 1, 2, 3, 4, but the other half gives you components in the order 3, 1, 4, 2. If you just compare components 1 and 3, you won't get a match. They will be different. So you have to compare all of them against all of them. You should also note that there is two different axes, the excitation wavelength axis and the emission wavelength axis, and you compare components in both axes. And in order to declare them the same component, you should make sure that they match in both dimensions, both in the excitation and emission mode. Also, how do you compare components? Tucker's congruence coefficient is very good at this because it has more or less the same properties as PARAFAC. It's scale invariant. So something that looks like this and something that looks like this, I think it should have Tucker's congruence coefficient of close to 1. But what it doesn't ignore is shifting. So something that looks like this and something that looks like this will not get a score of 1 because there is a constant shift between them. This is important because PARAFAC can be scaled, but I don't think you can easily shift PARAFAC models. For example, if you add a constant to a PARAFAC model, the constant will be represented as a whole separate component consisting of ones. It's not something that can be handled by existing components. There's also the question on how you should split your components. You can sample them randomly. Just shuffle them, then divide in half. And you can calculate the number of different halves you can get, and it's a very large number for large n. And some of those halves will be luckier than others. It's usually a good idea to use the metadata that you have about your samples when you perform split half. I've already said, well, I already mentioned on the slides that if you repeat samples, they should definitely go into the same half, because otherwise you might be tricking PARAFAC into giving you similar loadings despite the model is not right, and it should have been giving you different loadings. On the other hand, suppose you're on a research vessel. You've covered a large area of the map. You've been going like this and taking seawater samples. What you didn't know is that one of the components sits here and the other component sits here. And okay, maybe here they overlap, but there's little of both components here. And there's also one component here. If you're unlucky, your halves will be too different from each other. So what should help is label your samples with a group, with groups like these are from part A of our cruise of the research vessel, and these are from part B. And that's why, and let's try to ensure that when we're splitting our data set into halves, there is always something from group A and something from group B in each half. But we still should make sure that the halves don't intersect, because that's also trickery. That would make the loading simple, even when they would have been different otherwise. There's all kinds of formal criteria on what to do with the congruence coefficients. Once you have split your samples, fitted your models, matched the components, and finally compared them. This is what the comparison result looks like. I've taken 10 random samples, 10 random shuffles into two halves, then I fitted 20 halves, then compared the matching halves. You can see that these spectra are very different. There's probably not enough components, and you can see that Tucker's congruence coefficient is as low as 0.8. The 3-component model is mostly stable. some formal component, some formal criterion says you have to reach as high as 95% in order to say that your model is validated. When we look at this, we don't formally reach the criterion, but if you're a sea expert or a seawater expert, or there is some other prior information that you know about this data set, if you're sure that you're not in the local minimum, it might make sense to choose a higher component model with a lower Tucker's congruence coefficient, as long as it otherwise makes chemical sense. For example, 5-component model doesn't make sense. The shapes are too different. Noise starts leaking in the components. But the 4 components, if you're sure the 4th component is worth it, it might work. But in this case, I think I'll go with 3. I'd like to thank a number of people. We'll have a break after that. Thank you for listening and not interrupting me with questions. Thanks to Anastasia Drozdova for the logo I showed you on the first slide. To my colleagues Timur and Alexander, who gave me the C dataset, which I used in this talk. And to Rasmus for explaining me the second order advantage. I stole the explanation from him. After the 10-minute break, we can start the practice. If you're not sure you can run R or the packages that we'll need, you can ask me for advice. But if you can, we'll just meet in 10 minutes. My watch says it's 10:19. How about we meet at 10:30? Okay. Okay, my watch says it's 10:30. And let's try to do this in a more interactive manner. I'll be using the lowest common denominator, just the command line R, because there's lots of graphical user interfaces for R, and I would like to make sure that no matter what you're running, you can do it no matter what. You can be running RStudio, R graphical user interface, R for Mac, something else. As long as you run R code, you should be fine. Where to start? I've asked you to download a few files. The files listed here on the conference page. Has everyone downloaded them? The other important thing is that R has this implicit current directory thing. So in order for it to be convenient for everyone, let's change the directory to the files, to the one where the downloaded files are present. Ah, come on. This wasn't supposed to happen. Thank you. Thank you. Is this any better?
No, not yet.
Ah, I get it. I was sharing my desktop background instead of my desktop.
Now it's better.
Okay. Because when you say desktop, it's ambiguous. Think so. Okay, so you've downloaded the files, you've changed the directory, and when you run list files, you can see the downloaded files, right? Well, I guess I'll assume that you do.
Yes.
So there is an easy data set and a more complicated data set. Let's start with the easy one. It's stored in the directory called dataset, and it consists of the text file with absorbance data and a directory containing a bunch of also text files containing fluorescence data. Let's look at the text file containing the fluorescence data. It's a table. It has excitation wavelengths in the first line and emission wavelengths in the first column of every other line. By the way, is it really 2 a.m. in Canada right now?
Yes, it's just before midnight now.
Wow. I'm not a morning person, but you're my hero. You're attending my course despite it's well past bedtime. Okay, so it's a text file. And more importantly, it's a text file that can be read by standard R function called read table. Well, also it reads the first line that's the header. We can instruct it to read it like this, and then it will name the columns. But if there is fluorescence data in files that can be read, what? Never mind. If there is fluorescence data that in files that can be read by read table, we can import it. We can also look at it by reading it with a read table. It's a bit scary, lots of noise, but every scan is present. It's meaningful. So we can import it into Albatross. I'll be using the Albatross package. Just by giving it the file name and telling it to use the format table like this. Nothing happened yet, but we can have the X object now contains the excitation-emission matrix, and it's a matrix. And it has a bunch of attributes telling us the emission wavelengths, excitation wavelengths, and so on. Most of the objects in this package can be plotted by feeding into the plot generic. We can see the excitation-emission matrix that we just imported. Since all the files in the dataset fluorescence directory are in the same format, which can be read by read table, we'd like to import the whole dataset as some kind of single object. But first of all, how do we navigate the Albatross package? It's got a help page, which you can run by typing package $Albatross. It's got an introduction, and it's got the list of all functions that you can run. So if you get stuck, you can start with package $Albatross, and it will lead you somewhere you probably needed to go. For every single function, well, for the only function of the Albatross package we'll use so far, but for every one of them, there is a help page, which we can, again, run using the help system of the R programming language. And it lists every way you can call them. For example, I've been calling them on character strings, which are assumed to be file names, and then I told it to use the table format. Sorry if it's obvious for everyone. I'm just not sure how much should I be explaining, because I don't know your backgrounds. Let me know if it's obvious. Let me know if it's not obvious, and I should explain something better. Either way, there is a function called FEM list, which creates lists of fluorescence excitation emission matrices. And we can give it just a directory. We can tell it the format, and it will give us a list. The list will be named. The list contains the same kind of objects as before. And all the processing functions in Albatross package can work on lists of excitation emission matrices. But and of course we can extract individual objects and plot them or do whatever we want to them, but so far we can only plot. Let's also import the absorbance data right now. It's also a text file, also the kind that can be read by read table. So we'll just read it. Yeah, there we go. It's a data frame. For convenience, we'll transform the data set from a list of VMs into a data cube. Now, data set is an array. It's a three-way array with emission wavelengths in the first mode, excitation wavelengths in the second mode, and so on. Since it's a single object, not like a list of things, we can plot the whole data cube and get an explanation of what's happening inside the data set. Since we have this absorbance data, which is named the same way as the samples in the fluorescence data set, we can correct the inner filter effect by absorbance-based method. There is a function called FEM-IFE, inner filter effect, that does this. And when everything is all right, it's silent and it just does its thing. But suppose we did something wrong. let's break the absorbance data set. I'll rename the third column. It used to be sample B, but now it's not. Yeah, there it is. Now let's see what happens if we try to correct the inner filter effect. It tells us what's wrong. We need an absorbance spectrum for sample B, but since I renamed it, it's missing. But since the rest of the columns are named correctly, it refuses to use this missing column for the sample B. For some kind of safety, it will only proceed if all the named columns are present in the dataset. But now that we've corrected our fictional fluorescence spectra for a fictional inner filter effect, we can see what kind of correction we had to perform. There is a lot of absorption in UV part of the spectrum, up to 2 times. Okay. When you reach a correction factor of 2 in real life, it may be a sign of a problem that you might want to start diluting the sample. But here the data set is completely fictional, so it wouldn't be a problem. Do I have any? Okay. The next part would be correcting the scattering signal. And for that, we have FEM scatter function. Is the font size right? Can you read it? I can increase it if you cannot.
Yeah, it's okay.
Okay, thank you. So let's see. It asks us for the widths. And if you read the documentation, it asks us for the 4 widths. What's up with that? Okay, I printed the data set instead of plotting it. Okay, so the 4 widths are in order. Relay scattering, this straight diagonal line. Raman scattering, which is less intensive, but you can see in a lot of fluorescence data, and it's not trilinear, so you have to correct it. What we don't see in this data set is 2 lambda signal. We almost don't see it. It starts here, but if we continued measuring beyond 450 nanometers, we'll be seeing a copy of the Rayleigh scattering signal here. And it's also non-trilinear, and it has to be corrected, and, which is why we have width for 2 lambda Raman, 2 lambda Rayleigh, and 2 lambda Raman scattering signals over there. Recently, I've seen a spectrum with 3rd order Raman and Rayleigh too, but they had really low intensity. Maybe I'll add that in a future version. For now, I just cut off the non-interesting part of the spectrum. So far, I haven't observed interesting fluorescence in 800 nanometers, but it could be there. The more problematic thing would be what to do if you have 2 lambda fluorescence. It doesn't break the PARAFAC assumptions. It's still an outer product for every fluorophore, but now every component has 2 peaks instead of 1. I guess PARAFAC will just have to live with it. Okay, we've been plotting and discarding the data set. But we have more things to look at here. The next argument is method. And so far I've been just emitting scattering signal. Also, I haven't been removing it properly. I think I have to make it wider. Let's see, I'll leave zeros here and 15 nanometers. Is that right? Yeah. The highest intensity here is now lower. We don't see banding here, but let's check. Okay, maybe we do. Okay, 16. 70. Okay, I think I'm done. Okay, so we've removed the scattering signal. But as I've told you, leaving large undefined areas is bad for PARAFAC. It can start imagining things, which is wrong. So instead of just removing signal, let's try to interpolate it. There is a number of methods available to us, which is a P-chip, simple but sensitive to noise, lowest, requiring parameters, Krigging, very CPU intensive, but the profiles look good, and Whittaker, my personal favorite. Let's start with P-chip. P-chip is the same interpolation method as in the original paper on the use of interpolation in to remove scattering signal. And okay, this is too noisy for this method, and the scattering bands are too wide. If they were more narrow, P-chip would be good. If the spectrum was less noisy, P-chip would be good. But here you can see horizontal lines of different kind. I think this would distort our loadings. This isn't right. The next one is Lois. And okay, it's smoother. Maybe it's a bit too smooth. I don't know. But with Lois, we can play with parameters. There's a whole section of additional parameters here, which will be passed to individual methods. For example, P-chip can be interpolating by row, which we've been doing until now, by column, which we haven't tried yet. It also can try both and then compute the average. So, whoops, I forgot to quote the string. Okay, what? Okay, this is confusing. Let's not do it for now. I may have broken something. I'm not sure. Okay, when it comes to Lois, does this work? Yes, it does. I've set the span parameter, which is the neighbor area, to 0.25. It says use 25% of the whole spectrum when computing the local polynomials for every point that's missing. And you can see that it's far too smooth. It doesn't even connect the rest of the spectrum. Let's say 0.1. I guess that's better, but it's still too smooth. Okay, the other end is 1/100th. Ouch. Now it's unstable. It produces warnings. Yeah. 100th is too small. Okay, we could be playing with lowest like this for a long time. And you can see that 100th is too small, but 5 times that can also be considered not, okay, it's too smooth. So the optimum could be between 0.05 and 0.01. And maybe it's even individual for every sample. In some cases, lowest is best. I've been measuring its ability to recover fluorescence profiles. And for some samples, lowest has been the best, period. But for others, you can see it's really hard to find the optimal span value. Let's see. What does Kriging say? Careful, this can eat your whole memory. Or can be slow. I've tried to make this data set small enough so that it wouldn't be a problem. But with some methods, you just have to wait. And I'm on a comparatively powerful machine. So if you're on a laptop, this could take even more time than that. I can't wait. Just okay, what I'm going to do is take only a few samples. The first 3 would be fine. Almost there. Maybe I should have gone with 2. At least it gives you a progress bar. This is the reason I've added the progress bar to FEM scatter. Most of the methods are quick, but Kriging, no, Kriging is slow. Okay, there is a the scattering areas are a bit too positive. They are above 0. But the way they spread the fluorescence signal among the scattering bands, I think it's good. I think it's better than P-shape at least. But as we've seen, Kriging is slow. What else can we have? By the way, if you have a favorite surface interpolation methods, maybe I can add it here later, of course. Woodpecker. It does require tuning. Like I've been tuning some parameters here for a long time. Here, it's surprisingly, it imagines something in the scattering area that shouldn't have been here. But it can take the whole data set. It's relatively quick. And the results are physically meaningful as far as I can tell. So as long as we recognize that scattering interpolation is a trade-off, what method do you think you like most? We'll have to choose one and continue working with the data set. I hope I haven't lost you.
No, you haven't.
Okay, then I'm going to make a decision myself and say it's Whittaker.
Right.
And yeah, now we've done it. We've interpolated scattering. And it looks like this. What's next? I've been working with oceanologists, and oceanologists have this concept of fluorescence indices, which is a function of a surface. And if you work with humic substances and dissolved organic matter in seawater, you may find them useful. We have a function here called FEM index, which extracts all kinds of indices and peaks from every surface. It's an interesting question on whether you'd prefer to calculate indices before or after the scattering correction, because some indices do interfere with the scattering area. I even have a picture about this. Look. For example, the Higgs index, it's almost touching the scattering area. If it's too wide, it would be overlapping with it. But okay, let's say we correct the scattering first and calculate the indices later. FEM index, like all functions in this package, okay, most functions in this package can take individual spectra and return a named vector. Yeah, it's just a named numeric vector of values. You can see that some values don't make sense, but that's because YFI is way over here. And we don't have that measured. We stopped at 400. We can also feed the whole data set to it. Maybe I can just print it. Yeah, I can just print it. And it returns a data frame with sample in the first column and the values in the rest of them. So if you work with fluorescence indices, as some oceanologists do, I think it could be useful. The next question we're interested in is how to find out the number of components. And the answer is split half. And we can perform split half using the FEM split half function. It takes a lot of parameters. Let's just give it the number of factors, like we'll consider 2 to 5. Okay. It wants us to tell it how to split the data set into halves. We'll just make 10 random halves. Because as I generated this data set, there was no outliers, no groups to think of. And 20 PARAFAC models should be quick enough. If you don't want to overheat your computer, you can tell it to give you 5 random splits or something like that. There's also a trade-off in that if you don't shuffle your data sets enough, you may not be seeing the whole picture. But if you shuffle your data set too much, you get just a jumble of confused lines. And it's also hard to make decisions because of that. Also, it takes a long time. When experimenting with this, once I performed a 100 random shuffle split half, and I had to leave it overnight on a relatively powerful computer in the lab. And it still was very hard to make a decision because the experts thought one thing and the split half pointed to another thing. Okay, split half. It's an object, a complicated object. And like all objects in this package, we can plot it. The first plot is relatively simple. It just gives us the Tucker's congruence coefficients between matching halves. You can see that 5 components is probably right out, but I'm not sure about 3 and 4. How to find out how to plot our objects. If we say question mark plot, it gives us only the documentation for generics, none of which apply to Albatross functions. One option would be to see the help page for the function that produced the object. I always make sure to put the function and the plot method in the same help page. The other way would be to say question mark plot dot class name. It says the class is VM split half, which is the name of the producing function. I always follow this convention too. And it also lands us in the same help page that says how to plot the object. This is not very interesting. It's just 2 plots that I have thought about. One of this is the Tucker's congruence plot here, and the other is factors. Just draw all the factors on the same plot. Okay, this is not the right, 2-component model is not the right model because it has many peaks inside every peak. It tries to be all of them, but there's not enough components. 3-component model is strange. On the one hand, it is relatively stable. On the other hand, there is something wrong in the emission part of the spectrum for one of the components. But let's see if we go with the 4-component model. To fit the PARAFAC model, we can use the FEM PARAFAC function, which takes the data set and the number of components. And it also defaults to non-negativity in constraints. But if you'd like to, you can override that. I mean, in fluorescence, you almost always want non-negativity, which is why we set it. Okay, PARAFAC is relatively fast in this data set. Well, there is definitely something strange in the third component, but okay, this is not supposed to be happening. I think we've introduced artifacts when we were interpolating scattering area. There is very bright signal in the 250 nanometers area in the third component, while it was supposed to be just scattering there. Which we were supposed to be removing. So this is something to watch out for. I guess I'll spoil the surprise and say that when I generated this dataset, it was supposed to be a 3-component dataset. So 3 should be the right answer, but then we have this. Okay, what happens if we use the 4-component model? Okay, this doesn't look like the kind of fluorescence I was expecting. I guess the moral of the story is you should be very careful about interpolating scattering area, because then you can introduce artifacts like this. But there's something else we could try. And this is the experimental method I've mentioned once. My colleague Osman Drinnen called it FLAME. FLAME stands for fluorescence and scattering model estimation. We'll try to model fluorescence and scattering at the same time, which is why we're going to use this data set, not the third data set, which has the weird spot in the scattering area, which broke our models. So we'll try to model this. And there is a lot of controls, and probably more controls are lacking. This is all a bit experimental, but we'll tell it to use 3 fluorescence components, 1 scattering component, let's say 100 iterations, and stop when the relative change in R squared is less than 10 to the power of -6. Oh, it's thinking. This is what my colleagues call a psychological progress bar, because it doesn't actually know when it's going to finish. It only knows relative change in the loss function, in the sum of squared errors, and it knows that it's supposed to stop when it's 10 to the power of -6, or when we reach 100 iterations. But I'm not seeing it converge fast enough. Okay, maybe it will. What Flame does is basically modal fluorescence subtracted, modal scattering subtracted, and every other modal, when they alternate, they model each other's residuals. So they get the chance to take signal from one another. And sometimes, unfortunately, it can. The PARAFAC model can try to start modeling scattering. Or if you give too many degrees of freedom to the scattering model, it can try to take fluorescence from PARAFAC. Oh, I forgot to save it. There is a fix for that. In R, there is a hidden variable called last value, which is like ans in MATLAB, if you speak MATLAB, which you can assign to a different variable. And now we've saved the answer. And as usual, we can plot it. And this is what our signal was supposed to be looking like. Fluorescence components look like fluorescence, and the scattering only has scattering in there. The bright Rayleigh band and the not so bright Raman band. So we've solved the problem we've created ourselves by not interpolating the scattering signal correctly. What else can we do? There is a website called Open Floor. Okay, yeah, they changed the address. It's a data set, it's a database containing a lot of fluorescence models, PARAFAC models of fluorescence. There is an article about that. Let me, I can copy the link in the chat. Come on. So once you've done modeling your data, you can use the write open floor function to prepare a file for uploading into the database. What else can I show you in the remaining 15 minutes? I've showed you flame. I've showed you index. Maybe someone has someone has questions. Maybe you've been trying to correct scattering in a different manner and you managed to avoid the artifacts in the scattering area. I mean, I would like to fit this the right way. Because interpolation has been my bread and butter. No, I still get the artifacts. Okay, maybe if we use p-chip, no, it's damaged the profiles too much. Let's try it like this. We use split half on the same data set, same. Okay, this number of components, 10 random shuffles. I understand my colleagues now when they tell me that they don't like remote work. When you're just speaking at the LED in your web camera and hoping that someone's hearing you on the other end, it can be a bit isolating. Like you're on the International Space Station, for example. and you're not sure that everything is fine on the Earth?
Don't worry.
Okay.
Yes, don't worry, everything is fine.
Thanks. Okay. The four-component model is definitely out. It's all over the place. Some of it got stuck in local minima. The two-component model is not enough because it's trying to resolve different things, but it only has two components, so it doesn't manage. And the three-component model, which we know should be right, is still not stable enough. What's interesting about the split half object, I told you it's huge, but it's also documented. And I'll try to preserve its structure as documented. In particular, it has three components. One of them is small, it's just the numbers of factors. One of them is the Tucker's congruence coefficients to plot them. And the first one is the list of every individual model in this object, which we can individually plot. So let's take a look at SH dollar factors. I mean, it's a giant list, and it's a giant multi-dimensional list, but we can still handle it. Like the first dimension is half, the second dimension is number of factors, and the third dimension is the split. So the first half, the number of factors is 3, and which shuffle we take doesn't matter. Yeah, it's a PARAFAC model. We can plot it. We can plot everything here. Okay. Maybe we didn't let the model converge because we stopped it too early. Let's take a look at the other repeat. Okay, maybe. I mean, we have damage because of p-chip in the shapes of the loadings, but maybe we can fix it if we ask it to work some more. The default stopping criterion is 10 to the power of -4, which can be okay, too large, because the smaller the stopping criterion is, the more strict it is. So we can make it more strict. We're setting 10 to the power of -6. And you can see that it's now much slower because every model needs longer to fit. And this is probably the main factor in PARAFAC analysis. You just have to wait until you get the result. Some things in the package have support for parallel processing, but in my experience, the best speed up you can get, and this is about to get technical, is to install a speedy basic linear algebra subroutines package. Depending on your system, you can install OpenBLAS or Intel Math kernel library. And since every mathematical function in R uses BLAS, by just replacing the standard BLAS with a fast BLAS like OpenBLAS or MKL, you can let R utilize more than one core when computing PARAFAC. Like right now, it uses 40% of an 8-core processor. Hang on, how many cores do I have?
So is this helpful for any kind of R calculation or only for this PARAFAC package?
For every kind of matrix manipulation that R performs under the hood. So Inside is just matrix products and computing pseudo inverses, and BLAS can help you with that. So a faster BLAS can do all of this faster. On the other hand, I could imagine an R package that doesn't use matrix mathematics, so wouldn't benefit from installing a better BLAS. But then again, it wouldn't lose anything. Okay, I've got 4 cores with hyperthreading, and this is about as good as I can get with hyperthreading, because hyperthreading kind of doubles the number of cores, but then it's not quite possible to use them all at the same time. So for most purposes, 4 cores with hyperthreading is still 4 cores, despite they look like 8 cores. So 40 to 50% is fine. Okay, asking it to converge more strictly didn't help. I guess I've introduced too much in the way of artifacts. Maybe some other interpolation method or some kind of or other combination of parameters would help. I would say this is homework, but I wouldn't like to give you homework because this is a one-time course. So if you're curious about this data set, you may play around with it until you find a way to make a 3-component model that describes it well. If you have your own data, by all means, use your own data. Is there anything else you'd like to hear about? There are some other functions in the package that I haven't mentioned because they're a niche, like FEM grid lets you interpolate the whole data cube on a different emission and excitation wavelength grid. This is normally not important, but we had a very interesting fluorometer, which we later find out was miscalibrated. So the wavelength grid it told us about had to be changed, but then we couldn't combine the resulting data cubes with that after we recalibrated it, because the grids were incompatible. They didn't match. So in order to handle this, I had to implement some kind of interpolation method, which filled the gaps in both grids and let us combine the data cubes. If you ever find yourself in a situation like this, FEM grid could help you, but since it's interpolation, you have to be careful. Like if you have large missing areas, they will also get interpolated. And when interpolation methods get to extrapolate, they get very confused. What else? There's a built-in data set called FEMs, which gives you a small cube to test things on, a large list of fluorescence, excitation, emission matrices. It's the same one we've been playing with. It's just already packaged with the data set. And okay, as a bonus, if everyone has time, I'm sorry for taking a bit long, but let's try to import the DORA dataset, which is why I asked you to download the RMATLAB library. Okay, RMATLAB, read mat, Dorit mat. Dorit is a first name. I've never met her, but I've read her thesis. And of course, It's really complicated. It's an eigenvector dataset object decoded by R into a large list, but we can navigate it. We can make it work. Okay, this contains 3 objects, and EM is the one we're interested in. Let's see, data. Yeah, data is the 3-way array. So let's call it EM. We can plot it. Yep, it's an EM, but it's in the wrong order. But I don't mean wrong, but it's not the order that Albatross uses. So we can permute the array. Position these dimensions first, then the sample dimension last. Now the first sample can be plotted like this. Yeah, okay. But just the fluorescence values aren't enough. We'd like to have wavelengths. I just know that the wavelengths are stored in the axis scale part of the eigenvector dataset objects. Yeah, there they are. So let's say emission wavelengths are in the axis scale. 1, 2, yeah, the second one. And then the first one, because it's a nested list. There we go. Okay, it's a matrix. Let's convert it into a vector. Because R distinguishes matrices and vectors and sometimes gets confused. There we go. Now it's a plain vector. And now excitation wavelengths are just the next component here. There we go. Okay, we have EM, emission wavelengths, excitation wavelengths. Now we can create a cube object we'll be working with from the matrix, from the array, from the 3-way array here. Emission wavelengths and excitation wavelengths. Previously, we made it from a list of EM objects because we loaded individual files. Here we have a matrix and separate vectors of wavelengths, and we can also create a cube from that. Okay, now this is a EM cube, and we can plot it. There we go, the ORED dataset. This is yet another way you could import your data to work with it in Albatross. Okay, now it's definitely time for me to stop. It's been more confusing than I would have preferred, but I hope you got something useful from it. Do you have any questions? Okay, it's a Linux. Debian to be precise, but it shouldn't matter because R runs on all 3 major operating systems. Another question I might have is there anything that Albatross doesn't do yet, but you'd like it to do? Because so far I've been solving my own problems and the problems of my immediate colleagues. But if there is anything else, perhaps I could implement it. Maybe you'll find out if you try it on your own data set later. So since I'm not seeing any other questions.
Sorry, Ivan, I have a question.
Sure.
I had some technical problems, so
Okay.
I was not in time. So the first is, does your PARAFAC model imply any constraints except non-negativity? So can you introduce, for example, unimodality of emission spectrum or something like that?
I haven't tried it yet, but I'm using the multi-way package to perform the actual PARAFAC fitting, and multi-way supports a lot of constraints, including unimodality, and I think unimodality and non-negativity.
Yes, thank you. I see.
So it should be possible to pass a specific kind of argument to ask PARAFAC for unimodality.
Thank you.
Well, with that, you can always email me if you suddenly remember that you had a question but didn't have time to ask me. With that, I would like to thank you for listening again, and invite you to the next course, which will happen after some kind of break.
Thank you, Ivan. It was wonderful masterclass. I think it was very useful for everybody who connected our online courses. And yes, you're right. Everybody welcome to visit next short courses on independent component analysis provided by Yulia Monakhova. Thank you again for Ivan and everybody for attending our online courses.
Thank you. See you.